Okay, let's go over the proof of these four statements. In the first one I said use proof by contradiction to prove for every natural number little n, if n is bigger than 20, then n minus 8 is bigger than n over 3. So the idea is to look at the negation of this and get a contradiction from it. In other words, you should start by assuming that the negation of this statement is true. So you should say, suppose there exists a natural number little n such that n is bigger than 20 and n minus 8 is less than or equal to n over 3. Then what I did was I worked on this, the negation of this thing here, n minus 8 less than or equal to n over 3, and I deduced that if that's true, then it's impossible for n to be bigger than 20. So what I did was I simplified this by subtracting n over 3 from both sides and adding 8. So I say, from this inequality, if we subtract n over 3 from both sides and then add 8 to both sides, we get 2n over 3 is less than or equal to 8. And then multiplication of both sides of this inequality by 3/2 gives that n is less than or equal to 12, because 12 is equal to 24 divided by 2. And now you see we get a contradiction from the fact that n is also supposed to be bigger than 20, thus the original statement is true. In part B, I gave you this statement: for all pairs of real numbers x and y, if x and y are both rational, then x plus y is rational. I asked for a direct proof of that, so you should say, let x and y be real, suppose x and y are both rational, then we write down the working definition, then there exist integers a, b, c, and d, such that x is a over b and y is c over d, and since I wanted to say something about the sum, I then just simply calculated the sum. I put thus, x plus y is equal to a over b plus c over d. I combined my fractions and wrote it like this, and then I had to observe that since this numerator is an integer and this denominator is an integer, it follows by definition that x plus y is rational, and that completes the proof. In part C, I said use a direct proof to prove that for all natural numbers a, b, and c, if a divides b or a divides c, then a divides b times c. So I wanted to see that you could, first of all, give a direct proof, and second of all, you realized that this was a proof by cases. So there should be two paragraphs, one paragraph in which you deal with the first case in which a divides b, and the second paragraph in which you deal with the second case in which a divides c. So I say, let a, b, and c be natural numbers. Suppose that this happens. Suppose that either a divides b or a divides c. And then I said, we consider first the case that a divides b. I could have also just simply written case 1 period, suppose that a divides b, but I chose to write it this way. So either is very readable for the reader. So now in this case here, I write down the working definition, then there exists a natural number x such that b is a times x. And now since I wanted to make a statement about b times c, I look at this statement and see how I can get b times c out of it. I do that by multiplying both sides by c, and so I say, thus bc is equal to axc. I then regroup these terms in the way that will help me. I write it as xc times a, and then observe that since this x times c is an integer, it follows that a divides b times c. The other case is, suppose instead that a divides c rather than a divides b, and then I go through the argument in that case. It's similar to the argument in the first paragraph, so I won't say any more about it right now. Finally, let's look at my proof of part D, the limit statement. I've got the formal definition of this statement written on the previous page, but you'll recall what it was. So the first part of the proof has to be let epsilon be a given positive real number, And now I have to explain how to choose my delta so that the rest of the statement works. And of course that involves a certain calculation, which I'm not showing you here. And I won't go over that calculation with you now. But the ultimate justification is the fact that if I choose my delta in this way, then it works. But remember, you have to choose it to be a positive real number. So what I found to work is if I take my delta to be the minimum of 1 and epsilon over 3. And now I'm going to check that it works. So the next part is, let x be real. Suppose that absolute x minus 1 lies between 0 and delta. Then, and what I do is I have a certain string of inequalities, all of which I know to be true. And I begin with the left-hand side of the inequality I want to prove. I write. Then, I write down the left-hand side, and I observe that it simplifies to this, which factors like that. And we know that this factor here is smaller than delta from this assumption here. So that's why this is less than delta times. And now I start working on this absolute x plus 1. I write it like this in order to get an x minus 1 in the picture. I then apply triangle inequality to this second factor here. It's less than or equal to this delta times the sum of the absolute value of these two terms. I wanted you to make clear when you wind up using the triangle inequality, and so I've made that very clear by putting a parenthetical comment here. Now I observe that absolute x minus 1 is first of all smaller than delta, and which is in turn smaller than 1. So this piece is smaller than 1, plus the 2 that I already had. That gives me 3 delta, and 3 delta is less than or equal to epsilon by my assumption that delta is less than or equal to epsilon over 3, and that completes the proof.